From atomic nuclei to global power, nuclear energy. Let's be honest. The phrase nuclear energy has a personality. It walks into the room wearing a black suit, dramatic lighting, and everyone gets nervous. People hear nuclear and immediately picture mushroom clouds, alarms, and someone in a movie whispering, "We have minutes." But the real story starts in a place so small it's almost insulting. Inside an atom, in the nucleus, a tiny core that's basically the universe's most intense pressure cooker. So why does something microscopic end up having global consequences? Why does messing with the nucleus release energy that can power cities or terrify nations? Here's the simplest way to frame it. Atoms are not tiny billiard balls. They're tiny systems with rules, and the nucleus is where the serious stuff lives. Think of the nucleus like a packed stadium. Protons and neutrons are squeezed together so tightly that enormous forces are involved just to keep things stable. That stability has a price, and that price is stored energy. In everyday life, energy is usually stored in loose places: a stretched rubber band, a compressed spring, gasoline waiting to burn. Those are strong enough to move cars and launch rockets, sure. But nuclear energy is stored deeper, not in a chemical bond between atoms, but in the binding energy holding the nucleus together. This is why people say nuclear energy is dense. Not because it's emotionally intense, because a small amount of nuclear fuel can contain a ridiculous amount of energy compared to ordinary fuels. Now, how do we get that energy out? One major way is fission. Fission is when a heavy nucleus breaks into smaller nuclei, and when it breaks, the total binding energy changes. The after state can be more stable than the before state. That difference in stability shows up as released energy. If that sounded abstract, good. That means you're normal. So let's use a simple example. Imagine you have a pile of magnets stuck together in an awkward, strained arrangement. They're holding, but they're annoyed about it. Then something nudges the pile and it snaps into a more stable pattern. That snap releases energy as motion and heat. In fission, the nucleus is like that strained magnet pile. Certain heavy nuclei are stable enough to exist, but they're sitting in a condition where a nudge can make them split. And when they split, energy is released as kinetic energy of the fragments plus radiation plus heat. Now, one fission event is tiny, one single event. On its own, it's not powering anything except maybe the ego of a physics textbook. The real power comes from repetition, from a chain reaction. A chain reaction means one fission triggers more fission, because when a nucleus splits, it can release neutrons. Those neutrons can hit other nuclei, those nuclei can split. More neutrons come out, and suddenly you have a multiplication effect. This is the part people get wrong. A chain reaction is not automatically a bomb. A chain reaction is a mechanism. What matters is whether it's controlled or uncontrolled. Controlled chain reaction is like a campfire in a fireplace. It's still fire, it can still burn, but it's managed, it's limited, it has boundaries. Uncontrolled chain reaction is like lighting your entire living room on purpose and calling it home decor. Nuclear reactors are about control. Control over how many fissions happen per second, control over the neutrons, control over the heat removal. If you can control the chain reaction, you get steady heat. That heat boils water, the steam spins turbines, turbines generate electricity, and suddenly a tiny nucleus ends up charging your phone, running hospitals, and powering entire cities. So why is nuclear energy global? Because the physics is powerful and the consequences scale fast. One system can produce enormous output with relatively small fuel volumes. That changes economics, national strategy, energy policy, and public fear levels all at once. And yes, fear is part of the story, not because the science is evil, because humans are excellent at using powerful things in ways that deserve supervision. Now let's zoom in on the nucleus itself, because if you understand the nucleus, you understand why the energy is so intense. In normal chemical reactions, like burning wood or gasoline, you are rearranging electrons. Electrons are the outer social circle of atoms. They decide how atoms bond, how molecules form, and how chemistry behaves. This is the energy scale we live with every day. In nuclear reactions, you're not rearranging the social circle, you're changing the core, and the core plays by a different league of forces. Inside the nucleus, protons want to repel each other. They have positive charge, and like charges push apart. If the nucleus were only governed by electromagnetism, it would basically explode instantly. So why doesn't it? Because the strong nuclear force exists. It's one of the fundamental forces of nature, and it's absurdly strong at very short distances. It acts like a superglue, but only when particles are extremely close. So the nucleus is a balancing act, electromagnetic repulsion pushing protons apart, strong force pulling nucleons together. And the heavier the nucleus, the harder that balancing act becomes. At some point, certain heavy nuclei become easier to break into smaller pieces that are more stable. That's where fission becomes possible. Now here's a concept that sounds like a scam but is real: mass defect. When nucleons bind together, the total mass of the nucleus is slightly less than the sum of its parts. That missing mass isn't missing. It's been converted into binding energy. And that is where Einstein's famous equation shows up in the background like a quiet celebrity: E equals mc squared. You don't need to worship the equation, just understand the idea. A tiny bit of mass corresponds to a huge amount of energy, because c squared is enormous. That is why nuclear energy feels like cheating, because a very small change in mass-energy balance can produce a lot of usable energy. Let's do a simple analogy. Imagine you have a bank account where one coin equals $1,000. That's what nuclear energy is like compared to chemical energy. You don't need many coins to make a big purchase. But again, the trick is control. In a reactor, you want the chain reaction to be stable. That means, on average, each fission causes about one more fission. Not 0, not 5, just enough to keep steady power. How do you do that without turning everything into chaos? You manage neutrons. You use materials that slow neutrons down, because slower neutrons can be more likely to cause fission in certain fuels. You also use control rods that absorb neutrons. Insert rods, fewer neutrons available. The reaction slows down. Withdrawal rods, more neutrons. The reaction speeds up. It's basically a neutron dimmer switch, a very serious dimmer switch. The heat produced must also be removed continuously, because heat is the product you want, but it's also the danger if it accumulates. So reactors use coolants, pressure systems, and layers of engineering to move heat out safely and reliably. Notice what's happening here. The core science is simple in spirit: split nuclei, release energy, manage the chain reaction, harvest heat, make electricity. The complexity comes from engineering and safety, because the nucleus does not care about your feelings. It follows physics. If you want to use it, you must respect it. That's why nuclear energy sits in a weird place in public perception. It's one of the cleanest energy sources in terms of carbon emissions during operation, but it also requires trust in design, maintenance, regulation, and human competence. And humans, well, humans are creative, sometimes impressively, sometimes irresponsibly. So the real debate around nuclear energy is not, is the physics real? The physics is real. The question is, can society operate this technology with discipline over decades? Because nuclear energy demands long-term thinking, and long-term thinking is not humanity's strongest hobby. Now, let's address the elephant in the room. The word that makes every conversation about nuclear energy turn into a tense family dinner: weapons. We're going to keep this scientific and responsible. No how-to, no operational details, just the big picture difference that clears up the confusion. Nuclear weapons and nuclear power both involve nuclear reactions, but they are not the same type of system. The difference is like comparing a controlled burn in forestry to setting an entire city on fire. Both involve combustion. Only one is designed for disaster. A power reactor is designed to keep a controlled chain reaction going steadily, removing heat safely and producing electricity. A weapon is designed for a rapid, uncontrolled release of energy. So when people say nuclear is nuclear, they're technically right in the way of saying water is right. Sure, but a glass of water and a tsunami are not the same life experience. Now, why does nuclear energy feel world-changing? Because it sits at the crossroads of three things: energy density, national security, and public fear. Energy density means you can run a lot of power with relatively small amounts of fuel. That changes supply chains. That changes geopolitical dependence. That changes how countries plan energy stability. National security enters because nuclear knowledge overlaps with sensitive capabilities, and nations take that seriously. And public fear enters because nuclear accidents, though rare, are high-consequence events and get burned into cultural memory. But let's be fair, every major energy source has consequences. Coal has air pollution and long-term health damage. Oil and gas have climate impacts and geopolitical entanglement. Large dams can displace communities and alter ecosystems. Even renewables require mining, manufacturing, and grid planning. There is no energy source that comes with a halo and angels singing. Energy is always a trade. Nuclear energy's trade is this: high output, low operational carbon emissions, and reliable baseload power, in exchange for complex engineering, waste management responsibilities, and the requirement of sustained oversight. Now, about waste, this is another part people misunderstand. Nuclear waste volumes are relatively small compared to the waste streams of fossil fuels, but the waste can remain hazardous for long periods, so it must be handled, stored, and managed responsibly. That is not optional. If someone talks about nuclear energy while acting like waste is no big deal, they are selling confidence, not realism. But here's the twist: fossil fuel waste is also dangerous, and we have been dumping it into the atmosphere for a century like it's invisible. It's just spread out, so it feels less dramatic. Carbon dioxide doesn't glow, so people pretend it's polite. Nuclear waste is visible as a concept, so it forces accountability, and accountability makes people uncomfortable. Another misunderstood point is safety culture. In nuclear power, safety is not one feature, it's an ecosystem. Redundancy, training, maintenance, regulation, transparency, emergency planning, and the humility to assume something will go wrong someday and be prepared. When nuclear safety culture is strong, the technology can be operated with high reliability. When safety culture is weak, any complex system becomes dangerous. This is not unique to nuclear. It's true in aviation, medicine, chemical plants, and even bridges. But nuclear consequences are the kind people remember forever, which is why standards are intense. So the correct mindset is not blind love or blind fear. The correct mindset is informed respect. Nuclear energy is powerful because the nucleus is powerful. If you want to use it, you must treat it like a serious tool, not a toy, not a shortcut, not a political slogan, and definitely not something you let run on autopilot while everyone argues on the internet. So let's tie the whole story together. How does a tiny atomic nucleus become global power? Because the nucleus stores energy at a fundamental level. Because changing nuclear stability can release heat at a massive scale. Because a controlled chain reaction can deliver steady power for years. And because the same underlying physics, if misused, carries enormous destructive potential. That's the entire drama in one sentence. It's not magic, it's physics with consequences. Now let's make it simple with a final everyday picture. Imagine your city is powered by millions of small fires. That's roughly what fossil fuel systems look like. They burn and burn and burn, and the waste goes up into the air. It's constant, it's familiar, and because it's familiar, people treat it like background noise. Now imagine your city is powered by one extremely powerful furnace. That's closer to the nuclear model. It's concentrated, it's efficient, it's heavily engineered, and everyone watches it closely because the idea of one big thing feels scarier than many small things, even if the many small things are quietly harming us every day. Humans are emotional risk calculators. We fear what feels dramatic. We tolerate what feels normal. That's why nuclear debates get intense. They're not only about physics, they're about psychology, trust, and governance. If you take nuclear energy seriously, you end up with a balanced view. You recognize why it's attractive: reliable power, high output, low operational emissions, small fuel volumes. You also recognize the responsibilities: waste handling, long-term policy, strict safety culture, and strong oversight. And that's why nuclear energy is global power, because it's not just electricity, it's a system that touches politics, economics, climate strategy, national security, and public perception. Now, if you want the most practical takeaway from this entire story, it's this: the science is not the hardest part. Splitting nuclei and releasing energy is conceptually straightforward. The hardest part is operating complex systems with discipline for decades, because technology is only as safe as the humans who maintain it. So when someone asks, is nuclear energy good or bad, the honest answer is it depends on design, regulation, and the culture around it. Which is not a satisfying answer for social media, but it is the answer reality prefers. Now I'll end with one question. If you had to choose which power source to live near for the next 20 years, would you pick a coal plant, a gas plant, or a nuclear plant? And why? If you want more science explained with a sharp bite and real clarity, please like, share, and subscribe to Wiseuse.